In this lecture, we're going to start talking about totally unimodular matrices. We're eventually going to see how to use these in integer programming, but for now we're just going to introduce what they are, how to show a matrix is totally unimodular, and a few of their properties. So to start, a totally unimodular matrix is a matrix where every square submatrix has a determinant equal to 0, 1, or -1. This is just a definition, and in case you need a brush up, a submatrix is any matrix that we can recover from A by removing rows and columns. A consequence of this definition is that every entry in a matrix A that's totally unimodular is either 0, 1, or -1. Here we have two examples of matrices. Here we have a matrix A that's totally unimodular. And we could verify this by taking every square submatrix and computing its determinant and showing that it's equal to 0, 1, or -1. On the other hand, here we have a matrix A that's not totally unimodular. The determinant of the matrix itself is actually not 0, 1, or -1, so it's not totally unimodular since the matrix itself is a submatrix. This is the definition of a totally unimodular matrix. We'll see why they're useful in just a second. To show that a matrix is totally unimodular is pretty tedious to go through every submatrix and then compute its determinant. Really, that's just the definition. To show a matrix is totally unimodular, we're going to use two specific types of sufficient conditions. Note that these aren't necessary conditions. That is, a matrix can fail to satisfy these set of conditions, but still be totally unimodular. The first set of sufficient conditions verifies that every entry in the matrix is either 0, 1, or -1, that every column contains at most 2 non-zeros, and then finally, the sort of most complicated restriction is that we can partition the rows into two sets, M1 and M2, so that if we sum all of the entries along a particular column in the rows marked by M1 and subtract from that all the entries in that same column summed over the rows M2, that this sum is equal to 0. That is, we look at every column, we take the entries from M1, subtract the entries from M2, and this is going to be equal to 0. This is the first set of sufficient conditions, and usually it's a fairly useful one. However, it excludes a particular case that's actually very easy to identify. If, for example, we have a matrix where every entry is 0, 1, or -1, and every column contains at most one non-zero, this matrix is also going to be totally unimodular, but it's not considered in the sufficient conditions 1. These conditions, sufficient conditions 1 and sufficient conditions 2, are going to be the main tool we're going to use to show that any matrix is totally unimodular. Here we have properties of totally unimodular matrices that all turn out to be equivalent. And these properties can be thought of in two different ways. Some of these properties are going to help us show that particular matrices are totally unimodular. The other set of properties is going to let us exploit the power of totally unimodular matrices to show that problems are easy to solve. The first property that we're going to show in this set of equivalences is that A is totally unimodular. This is sort of our baseline. We know that if A is totally unimodular, also that the transpose of that matrix is totally unimodular. We also know that appending the identity matrix in sort of a block matrix format is also going to result in totally unimodular matrices. And finally, any submatrix of A is going to be totally unimodular. We're not going to prove these properties, but it's pretty easy to show these properties by using the basic definition of determinants. All of these properties are going to help us show that when we look at a constraint matrix, this constraint matrix actually has a totally unimodular constraint matrix. Specifically, we're going to look at appending identity matrices, taking transposes. These are going to help us prove things. The second set of properties are going to let us exploit the power of totally unimodular matrices. The first property is that if we have a totally unimodular matrix A, then the inverse of that matrix is an integer matrix. And this is key. We'll see why it's key later. The second property in this category is that if we have a totally unimodular matrix A, and we use this matrix A as our constraint matrix to a linear program, then that linear program has an integer optimal solution. And we can see exactly why this is going to be important to us. If we have an integer program with a totally unimodular matrix as its constraint matrix, and we take the linear programming relaxation, we haven't lost anything. That is, if A is totally unimodular, we look at the integer programming solution, and it's actually equal to the linear programming solution. This is why we talk about totally unimodular matrices. When they're embedded inside of an integer program, we can actually show that that integer program is an easy problem to solve because we can just solve its linear programming relaxation. We'll actually prove why this is the case later on because it's quite interesting. For now, we're just going to say that these are the properties of totally unimodular matrices and that we'll use them in the future.